So good morning one and all. So let us start today's class. Yesterday, in the last class, we have started with the introduction to the deep learning. Now as I told you, we are following the NPTEL videos by Professor Mitesh. Now you can watch these videos from this link. I told you deep learning is the subset of machine learning. In deep learning, we try to learn just like the humans learn. We design a machine which can learn like a humans. Now this is about introduction, and we get a motivation from the biological neuron. That is a basic element of a nervous system of a human brain. Now this is the typical biological neuron which has got some parts I explained in the last class. Now here, how does the neuron work? So basically there is a parallel layer of neurons. There is a hierarchy of neurons. Neurons will pass electrical signal, then we call it as a fired. Whenever neuron passes electrical signal, we call it as a neuron is fired. Okay. Now obviously we have a layers of neurons, multiple layers, and they are parallelly interconnected with each other. So the first layer will be interacting with our sensory organs, and whenever the incidence is funny, so they will fire, and so on will happen here. So all the neurons which are shown in red are fired. So if what you see is funny or what you hear is funny, what the action is, about the action, laughing. Okay. So the action will be initiated based upon the input. If input is funny, obviously the action will be initiated. Who will decide? So neurons will decide whether to take action or not. Okay. Now next. So yeah, in the same way, so this is the visual cortex. As I explained in the last class, it is a part of the brain which processes the visual information. So this is the path, and obviously in the brain we have a high level of processing. Okay. So the disclaimer, obviously nobody can understand the brain perfectly, but what we see in this course is efficient and sufficient at the same time for our course. Anyway, so as I told you in the last class, Michaelis-Spitz come up with a mathematical model for the biological neuron. So this is the mathematical model of a biological neuron that is given by Michaelis and Spitz. We simply call MP neuron. It has two parts, G and F. The first part is the aggregation. It aggregates all the inputs. Second part takes the decision based on the sum value or based on the aggregated value. So here the inputs and outputs happen to be Boolean. Okay, what are they? They happen to be Boolean. So now, yeah, so whenever neuron is fired, we call it as 1. 0 means the neuron is not fired. Now, so as I told you, the inputs are two types: inhibitory and excitatory. Okay, inhibitory means they have a maximum effect on the outcome irrespective of other inputs. As I told you in the last class example, so whenever you want to go to a movie, so but you are sick, so the particular input is X3, let us take, that is you are sick. Now irrespective of what is the who is the hero, who is the heroine, or who is the director, or whatever it is, you cannot go to the movie because you are sick. Now because the sickness is the predominant in this case, that will decide the output irrespective of other inputs. Okay. Now that is called inhibitory inputs. One more thing is, whenever inhibitory is 1, the output is 0. Whenever there is a inhibitor input that is on, the output is 0. Excitated inputs are not the one which can fire the neuron on their own, but the collection of several excitated inputs can fire the neuron. Okay, remember, whenever inhibitory input is on or it is 1, the output is 0. Okay, because it is having the maximum effect on the decision making irrespective of other inputs. Now there is a thresholding logic. Obviously, whenever the sum is more than the threshold, the neuron will fire, otherwise the neuron will not fire. Here theta is called the threshold. So we can decide the threshold based upon our requirements. Now, so let us start with the Boolean function using MP neuron. Boolean functions using MP neuron. So what we do is, we implement a Boolean function using this neuron. Okay. So let us start with the first one. Here we have 3 inputs, x1, x2 and x3. Okay. We have 3 inputs. What are they? x1, x2, x3. Now what is, this is the input. Now what is g of x? G of x is sum of all inputs. xi, I varies from 1 to 3. Now what is this? G of x is x1 plus x2 plus x3. This is called aggregation. What is called? Aggregation. Now, so simply this is theta. Simply that is theta. Okay. So what happens? So theta is nothing but sum of all the inputs or sum. So whenever the sum is more than theta, okay, whenever this sum is more than theta, whenever this sum aggregation is more than theta, okay, the neuron will fire. What will happen? The neuron will fire. Fire means the output is 1, otherwise the output is 0. So let me simply explain this with an example. Yeah. So in the previous case we have 3 inputs, x1 plus x2 plus x3. This is nothing but sum. Okay. So whenever the sum is more than the threshold, output is 1. Otherwise output is, whenever sum is less than threshold, output is 0. So what do we say here? In this case, the neuron is fired. Here it is not fired. Okay. Now, next. So let us go with AND function. Okay. So in the case of AND function, what will happen? Output is 1 when all the inputs are 1. That is the logic of AND gate. You know AND gate, right? AND gate output is 1 when all the inputs are 1. Correct? Now, so here we have 3 inputs. When all the inputs are 1, what is the sum? What is sum? 1 plus 1 plus 1, that is 3. So sum is 3. Okay, here theta is 3. Now, so the AND function neuron would fire only when all the inputs are on. Obviously, the AND gate neuron will fire only when all the inputs are on, or when all the inputs are 1. When all are 1, what is the threshold? Sum of all the inputs, that is 1 plus 1 plus 1, that is 3. Here, don't take Boolean addition. Okay, that is not the case. Simply add all the inputs. Okay. Now, what is this now? What do you say now? G of x is, in this case, what do we say? G of x is theta is 3. So what the logic? Simply it becomes, when g of x is greater than equal to theta, that is 3 in this case, the neuron will fire. Otherwise, whenever is less than theta, that is 3, neuron will not fire. That is a AND gate with neuron effect. Okay, simple things. Next, OR function. Obviously, whenever at least one of the input is 1, the output is 1. That is the logic of OR gate. So we know that then OR function neuron would fire if any one of the inputs is on. We have 3 inputs. If at least one of the inputs is 1, the output is 1. Which means the OR function neuron will fire if and only if at least one of the inputs is I. Okay. So if any one is I, that means if any one of the inputs is 1, the output is 1. Which means the neuron will fire. Now what is the threshold? Threshold means minimum value. So minimum should be any one of the inputs should be I. Okay, which means so here either x1 or x2 or x3 should be 1. At least one should be 1. Remaining can be 0. So what is the threshold? Threshold is what? 1. Okay, 0 plus something like this. It is 0 plus 0 plus 1. Okay, only one in at least one of the inputs is 1. Remaining can be 0. So what is the threshold? 1. So threshold is 1. Okay. Now what do you say? So it will fire. So g of x should be greater than or equal to 1. If it is greater than or equal to 1, the output is 1. Otherwise, the output is 0. The neuron will not fire. That is simple logic. Next. Okay, now, so just now I explained the importance of inhibitory input. Whenever the inhibitor input is 1, the output is 0. Otherwise, whenever the inhibitor input is on, the output is 0. Okay. Now, let us take, now the inhibitor input is indicated with circle. So, that is indicated with a circle. Yeah, here in this example, this is the inhibitory input. Because it is indicated with the circle at the end. Okay. Now it is AND gate with inhibitory input. Okay, x1 and x2. Okay. Now, so by logic, whenever x2 is 1, output is 0, irrespective of x1. That is the main reason for inhibitory input. Okay. Now, so let us go with the logic. Now, whenever x2 is 1, the output will be 0. Now, when the output is 1 now, we know that output is 1 only when what is the possibility? You think of possibilities. So, for output to be 1, it should be 0 and it should be 1. Is it okay? So, suppose see actually we get 4 possibilities. What are they? 0, 0, 0, 1, 1, 0, 1, 1. x1, x2. Okay. So, x2 is inhibitor input. It should not be 1, which means these 2 cases are taken out. Okay. In remaining 2 cases, what is the possibility? This is a possibility because it's AND gate. So, x1 should be 1, x2 can be 0. Now, in this case, the output is 1. Is it okay? Now, what happens here? So, what is this? This is the sum. What is sum? 1 plus 0. That is 1. This is the threshold, theta. Now, what do you say whenever g of x? G of x means what here? So, please remember, if I write g of x means that is aggregation or sum of all the inputs. So, g of x is nothing but x1 plus x2. Okay, here what is the threshold? Threshold is 1. Correct? Now, okay, next comes the NOR function. You know already, NOR means what? The neuron will fire when all the inputs are 0. Okay, so now NOR gate is what? When all the inputs are 0, the output is 1. Okay, now, so when all are 0 means, what is the sum? 0 plus 0 plus 0, sum is 0. Is it okay? Now, so here we take all the inputs as inhibitory inputs. All inputs are inhibitory. Why? Because, so whenever the input is 1, suppose if x1 is 1, output is 0. Otherwise x2 is 1, output is 0. If both are 1, output is 0. Okay, all the inputs are happen to be inhibitory, because if any one of the input is on, the output is 0. Correct? Okay, now all the inputs are inhibitory in this case. What is threshold? 0. This is a NOR neuron. Okay, so till now we have seen AND or NOR neuron. Okay, you can also see all the Boolean neurons that are possible with 2 inputs or 3 inputs. NOT function. Okay, obviously NOT function, if input is 1, output is 0, and output, if input is 0, output is 1. Okay, so whenever output is 1, for output to be 1, input should be 0, which means, so whenever input is 0, output is 1. Whenever input is 1, output is 0, which means the input itself is a inhibitory. Okay, what is threshold? So whenever it is 0, the output is 1. So only one input is there, there is no sum, so simply the threshold is 0. Is it okay? Right. Now, so next comes the important topic, that is geometric representation of a MP neuron. Now, till now we have seen simply what is the threshold and all those things. So let us see the geometrical representation of a interpretation of a MP neuron. It is very, very important to represent them geometrically. Okay, let us see. So let us go with the R function or neuron. Okay, so what will happen there? I am taking 2 input R function. Okay, x1 plus x2. What is theta? Equal to x1 plus x2. So obviously based upon the aggregated value or some value, we take the decision. What do we say here? So x1 plus x2 should be greater than or equal to 1. But so geometrically, what you can say is, you can draw all the points on a 2-dimensional plane, 2-dimensional axis. So here what is the thresholding factor or thresholding logic? It is 1, because any one of the input can be 1. That is the OR logic. So here 2 inputs, so 4 possibilities. Okay, what are they? 0, 0, 0, 1, 1, 0, 1, 1. Now here we can draw the decision boundary. Okay, this is x1, x2. What is the line? x1 plus x2 equal to 1. Let us draw this line. Okay, this is a line. What is this line? x1 plus x2 that equal to 1, that is theta. This is theta. Okay, now I am representing all 4 points on a 2-dimensional axis, 0, 0, 1, 0, 0, 1, 1, 1. Please remember, it is not a real plane. I am only representing 4 Boolean points on a 2-dimensional axis. Okay, we cannot represent 0.5 something like this here. We cannot represent 0.5 on this line because 0.5 does not exist in our Boolean case. We need only 0 and 1. That's it. Okay. So just remember that we are just representing 4 points on a two-dimensional plane, 2D graph. So mind you, this is not a real number graph. I am just representing 4 points on a 2D graph. Okay. Now, so this line, now what happens here? What do this line indicates? Now it is dividing the plane into two halves. Okay, this line is dividing the points into two halves. Okay, let me draw here like this. Okay, so this is something 0 0. This is 1 0, 0 1. This is 1 0, somewhere here 1 comma 1. Now there are two parts, above the line and below the line. Okay. Now what is happening here? Okay, so when those inputs whose output when passed through the R function MP neuron lie on or above that line, and all the inputs that lie below the line are going to get output as 0. It means the point which lies on or above the line, the points which lie on or above the line will get output as 1. Okay, this is a decision boundary. It is something like decision boundary. Is it okay? It's a boundary. This line is a boundary. Which means the points which lie on or above the line will get output as 1. The points which lie below the line will get output as 0. Which means here among 4 points, 3 points lie on or above the line. This point lie on the line, on the boundary. It also lies on the boundary. It lies above the line. So all these 3 points will get output as 1. So the points which lie below the boundary will get output as 0. Isn't it? Okay. This is called geometrical interpretation of a MP neuron. We get a boundary. So if the point lies on or above the boundary, the output is 1. If they lie below the boundary, output is 0. Obviously, for these 3 inputs, output is 1. For the fourth, this is 0 0, output is 0. That is our logic. Okay. Now, so we can divide the set of inputs into two parts, two types. That is positive and negative. So the points which lie on or above the boundary are said to be a positive input because the output is 1 for them. The points which lie below the boundary are said to be negative inputs because for those points the output is 0. Okay. So this is called decision boundary, and we have seen the geometrical interpretation of a R function neuron. Okay. Yeah. In the same way, you can try for the AND gate, AND function. Okay. What you can say? So AND gate, I have taken 2 input AND gate here. So the output is 1 whenever all the inputs are 1. That is the logic of AND gate. So here 2 inputs should be 1. When the given 2 inputs are 1, the output is 1. So obviously what is the threshold? 1 plus 1, 2. As I told you, don't go by logical addition. Just add them. 1 plus 1, 2. Okay. This is a threshold. So x1 plus x2 is, what is the logic now? Threshold theta equal to 2. Whenever the sum x1 plus x2 is greater than or equal to 2, the output is 1, otherwise whenever it is less than 2, the output is 0. Now here what is the logic? What is the line? We have to draw x1 plus x2 equal to 2. That is the line we have to draw. Yeah. So this is a line we can draw. This line is x1 plus x2 equal to 2, that is equal to theta. Okay. Now it is a boundary, decision boundary. Obviously it is dividing the 2D graph into two halves, two parts. Now among 4 points, 4 inputs, only this input lies on the boundary. Okay. So remaining these 3 points, these 3 inputs lie below the boundary. Obviously for these 3 points output is 0, for this point output is 1. Simple logic, because it lies on the boundary. Remaining 3 points they lie below the boundary. Now they are said to be, they will be called as positive inputs and it is a negative input. Okay, I hope you can understand this. Right, next. So we have something called tautology, which means, so we need a neuron which is always on. Irrespective of input, it should be always on. There is a mistake here. Something like this. So we need x1 and x2. We need output which is always 1. Okay, which means output should be 1 irrespective of inputs. Okay, output should be 1 irrespective of inputs, which means what is the threshold? Even though both are 0, output should be 1. Okay, input can be any value, output should be always 1. That is called tautology. Always on. Here what happens? Suppose, what is the threshold? 0. Threshold is 0, because even though both are 0, the output is 1. Output should be 1. Okay, so that is x1 plus x2 should be greater than or equal to 0. This is theta. So x1 plus x2 should be greater than or equal to 0 means, what is the line? We have a line here. So this line. Okay. Something like x1, x2 equal to minus x1. Okay. So x1 plus x2 should be equal to 0. Now, here what happened? 0, 0 lies on the boundary. This is the boundary now. 0, 0 lies on the boundary. Okay. What about remaining 3 points? They lie above the boundary, which means all 4 points lie on or above the boundary, which means all the inputs will give output as 1. That is a always on tautology. There is no input which can give 0 output. Geometrically, all the points lie on or above the decision boundary. Okay. Right. Next. So R function with 3 inputs. Till now we have seen all the Boolean functions with only 2 inputs. You can extend to more than 2 inputs, like 3 or 4 inputs. So if the 3 inputs are there, we have 4 points, obviously 0, 0, 0, all those things, you know, right? Now here we get a 3D graph, 3-dimensional. We go for 3-dimensional. Now it become a plane. Okay, obviously whenever you go for 3-dimensional or 4-dimensional, it become a plane. Okay. Now in this case of 3 input OR gate or neuron, what will happen? Okay. So here the input is 3 inputs, x1, x2, x3. So our logic is at least one of them can be 1, then output is 1. If at least one of the inputs is 1, output is 1. Okay, we have 3 inputs, any one can be 1. So what is the threshold? Threshold is 1. Threshold means minimum value so that output is 1. What is threshold? It is a minimum sum so that the neuron will be fired. Okay. Now obviously, so what will happen here? So theta equal to 1 and x1 plus x2 plus x3 should be greater than or equal to 1, that is theta, then output is 1 obviously, otherwise output is 0. Now here what is the plane? x1 plus x2 plus x3 equal to 1. You have draw this plane. Now I have taken a 3D graph. I have indicated 8 points like this. Okay, all 8 points starting from 000 to 111. Now this is a plane. This is a plane indicating x1 plus x2 plus x3 equal to 1, that equal to theta. Okay. Now here, so here what is the boundary? Plane is a boundary. In the previous cases, the line was boundary because it is a 2D graph. Now in 3D graph, the plane is a boundary. Now here, what is the logic here? You can see 7 inputs. Okay, you can see the 7 inputs. You cannot see one input, that is 000, which means the plane is dividing the inputs. Okay, so you can see 7 inputs. They lie on the one side of the plane, and the one input that you cannot see lie on the back side of the plane, that is all zeros, 000. Okay, which means so all the points lie on the one side of the plane, all the 7 points. Only this point 000, this input lie on the other side of the plane, which you cannot see in this figure. Okay, what do you mean by that? Okay, all the points lie on the one side of the plane are giving output as 1. Okay, so the one point which lies on the back side of the plane is giving output as 0. Now there is a clear division of the points. What are the points? Positive points, negative points. What you can see here is positive points because all the inputs will give a 1 output. They lie on the one side of the plane. So the output, the negative output, which gives 0 input, lie on the other side of the plane, which you cannot see in this 3D plane. Okay. Now here there comes the linear separability. Okay. There exists a line or plane such that all the inputs which produce 1 lie on the one side of the line or plane, and all the inputs which produce a 0 lie on the other side of the line or plane. Okay, so then it is called a linear separability. Now till now we have discussed Boolean functions which can be linearly separable. Linearly separable means there can be a line or a plane. Line means if it is 2-dimensional line, if it is more than 2-dimensional, it is a plane. Now there can be a plane or line such that all the points lie on the one side of the line will produce the output 1, and all the points which lie on the other side of the line will produce the output as 0. There is a clear division of the inputs by a line or plane based upon their outputs, something like this. Suppose it can be something like this. We have a 2-dimensional plane. So 2-dimensional plane. Now this is the boundary. So what do you mean by this? So there is a clear division of the points. Now the points which lie on this side may give output 0. Now the inputs which lie on the other side of the line may give output as 1. Now they are said to be linearly separable. These inputs are linearly separable because we can separate them based upon their inputs, based upon their outputs by a line or plane. If it is 2-dimensional, line. If it is more than 2-dimensional, we need a plane. Just now I explained in the case of 3 input OR gate. Okay. Now we are discussing, as of now we are discussing with Boolean function with linear separability. Okay. Now this is about MP neuron, implementing a Boolean function with MP neuron. Okay. So we stop here. Thank you.